let's consider now what would happen if we did one for germanium. So again, just like before, let's start our way at the top and work our way toward germanium. So that would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 10. Then we've now re-entered the 4p, so this will be 1, 2. So we went through the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. We had all 10 electrons in the 3D, so that got us up to here. And then we're 1, 2, 2 elements into the 4p. So we'll denote that as a 2. Now, the way we've been writing these descriptions for where the electrons are in our atom, this has been called the electron configuration notation. Now, let's suppose we didn't want to have to write all of this out every single time. Well, then we can use a shortcut known as the noble gas notation. So let's just practice how this works for germanium. So in order to use the noble gas notation method, what you're going to do is first locate your element of interest. In this case, it's germanium. Then you're going to go up to the previous row on the periodic table and find the noble gas that ends that row. So the noble gases are the things in column 18. So here's germanium. So we go up a previous row and find the noble gas ending that row, which in this case happens to be argon. So what we're going to do is put that noble gas in brackets. And so what that's going to represent is the electrons all the way up to argon. So this argon is going to take the place, so let me highlight this. So as we're working our way to argon, it's going to take the place of 1s2, 2s2, 2p6, 3s2, and 3p6. Alright, because if we worked our way to argon, that's exactly what we would get. 1s2, 2s2, 2p6, 3s2, 3p6. So that gets us up to argon, and then you're just going to pick up with the normal electron configuration from there. So here's where we've stopped so far. Now let's keep going. So we go to 4s2, 3d10, then we're back to 4p, 4p2. Alright, so this is known as noble gas notation, and again it's just using a shortcut, using the noble gas on the previous row to account for some of the earlier portion of the electron configuration, and then you just finish up with whatever's remaining. Okay, now there's one other method that we can use to write electron configuration. And that's known as the orbital diagram notation. And what this is it's very similar to what we did before when we were using lines to represent the orbitals within a subshell that the electrons could occupy. So let's consider how that works for something like germanium. So for this 1s orbital, we're going to represent it as a box because we know for the 1s subshell, it can only have one orbital, and that orbital can hold 2 electrons. Now, based on the Pauli exclusion principle, I have to draw one electron that's spin up and one that's spin down. Now let's keep moving on. Again, for 2s, it should just be a single box because there's only one orbital within that subshell. Since it has 2 electrons, I'll again fill it, one spin up, one spin down. Now, let's move to the 2p subshell. So we know that the 2p subshell has 3 different orbitals, each of which can hold 2 electrons, and that's where we get the total of 6. So let's fill those. And again, when we're filling these, we want to follow our rules. So Hund's rule states that the electrons must be singly placed in an orbital before we can double up. So let's place our 6 electrons. 1, 2, 3, 4, 5, 6. Alright, now let's keep going. Now we're back to the 3s, which will just be a single box because there's one orbital within the 3s subshell. It has 2 electrons, one will be spin up and spin down. And again, I'm just going to label this germanium. Now, next we come to the 3p. Sorry, I'm running out of room here. Alright, so here's our 3p. Again, the 3p subshell has 3 orbitals, each of which can hold 2 electrons for a total of 6 electrons. Let's place the 6 electrons that we have. 1, 2, 3, 4, 5, 6. Alright, now we get to the 4s. Again, one box with 2 electrons. Now we come to the 3D. And if we remember from previously, our 3D subshell can have a possibility of 5 orbitals, which would lead us to a total of 10 electrons if we place 2 electrons in each orbital. So here for the 3D, I'm going to represent this as a subshell with 5 different orbitals. And again, it's completely filled, so I'll now fill in my 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we're left with the 4p, which again, 3 orbitals. But this time our 4p subshell only has 2 electrons. So according to Hund's rule, I'll place them singly in orbitals instead of doubling them up. And so this would be the orbital diagram notation for germanium. And the orbital diagram notation is actually pretty neat because it kind of gives us more information and lets us get a better visual for how the quantum numbers relate to electron configuration. So the 1, 2, the 3, and so on, like the principal quantum number, those show us the energy level. Then the S, P, D, and F narrow us down to a subshell. Then, within those subshells, we can see there are different orbitals. Within the S subshell, there's 1 orbital. In the P subshell, there are 3. And that's our 3rd quantum number. And then lastly, our 4th quantum number tells us that within an orbital, 1 electron must be spin up and the other spin down. All right. So I hope this was helpful to you all, and thanks for listening.